Before we introduced the expected utility model, we discussed the idea of Dutch books as a certain pattern of behaviour regarding choice under risk that we would like to exclude. The axioms for rational behaviour for choice without risk, which were just completeness and transitivity, failed to rule out certain patterns of behaviour for choice under risk that we wanted to exclude. We know that there are complete transitive preferences that are subject to Dutch book type of behaviour, and this is not the case for expected utility. So when we say we are going to assume expected utility holds, we are essentially making more assumptions about behaviour. That is, we're going to add more axioms to our framework for decision making. So axiom 1 and axiom 2 were completeness and transitivity. We're now going to discuss the additional axioms that we will impose on preferences once we're considering choice under risk. The first new axiom that we're going to impose, our axiom 3, adding to completeness and transitivity, is called the mixture monotonicity axiom. Okay, so what does this axiom say? Well, the formal statement is the following. For all lotteries P and Q, where one of the lotteries we've labelled P is strictly preferred to Q, if we then look at compound lotteries where you either receive the lottery P or you receive the lottery Q, then whichever lottery gives you the best chance of the thing you prefer the most is the preferred lottery. So in this case, I've written two compound lotteries. The first on the left-hand side has probability RP, R of P, of getting lottery P, which is the better lottery, and probability 1 minus R of P, which is R of Q, of receiving lottery Q. Compare this to the lottery on the right-hand side. In this lottery, you also have some chance of receiving lottery P or lottery Q. In this case, there is probability S of P attached to the likelihood of receiving lottery P, which is the better outcome. So when I look at these two compound lotteries, I say, well, which of these is assigning the best probability, the highest probability to the better lottery P? So I prefer the left lottery to the right lottery if and only if R of P, the probability of P in that lottery, is greater than or equal to S of P. To give a simpler, more specific example, suppose that a decision maker prefers £100 to £50, where both are offered with certainty. So this is not a very difficult assumption to accept. £100 is preferred to £50. Well, then if I look at the lottery where I receive £100 with probability P or £50 with probability 1 minus P, the mixture monotonicity axiom states that making P as large as possible makes this lottery better and better. Okay, so as P increases, this lottery gets better and better as we attach more and more probability to the best outcome of £100. The next axiom we will add to our list of axioms for rational behaviour under risk is called the reduction axiom. Now, this axiom will essentially serve two roles. First of all, it's going to express the idea that all that matters to this decision maker is the outcomes they're going to get and the probabilities with which they get those outcomes. So it's a form of behaviour known as consequentialism. In a sense, if I'm looking at compound lotteries with many stages of risk that need to resolve, these don't really bother me. All that bothers me is what's the probability that I get a certain outcome and what outcomes are possible under this lottery when I compare it to different lotteries. So the first idea expressed by this axiom is something that we might call an idea of consequentialism. All that matters is the outcomes and their likelihoods. The second idea expressed by this axiom is that our decision maker understands probability calculus, so they are able to calculate probabilities in the correct way. So the statement of this axiom looks a little complicated, but it's capturing those two ideas: the idea of consequentialism, only the final outcomes and their likelihoods matter, and the idea that the decision maker understands probability calculus. So let's explain the axiom. The formal statement of the axiom is this: if we take a compound lottery P, which has some probability P of Q1 of getting the lottery Q1, and so on up to probability P of Qj of getting the lottery Qj. And then if I look at another lottery P hat, which is a simple lottery, which just assigns probability P hat of X1 to prize X1 up to P hat of XK to prize XK. Well, if I look at the probabilities of receiving each outcome under P hat, if they happen to be the same as the probabilities of receiving the outcomes under the compound lottery, where we're going to calculate those in a second, then I'm indifferent between these two lotteries. So if I look at the compound lottery P, I can ask, what is the probability that I receive outcome Xi? And we did this in an earlier video. We simply we do this reduction exercise where we say, well, with some probability P of Q1, I get lottery Q1, and then, so I multiply. If I get Q1, the probability is Q1 of Xi that I get outcome Xi. So that's one way in which I can receive outcome Xi when lottery Q1 happens. And then I add up all of the remaining possibilities up to some probability I get lottery Qj, in which case there's a probability Qj of Xi that I receive outcome Xi. So this is the probability of receiving outcome Xi under the compound lottery. If this is equal to P hat of Xi, so it's the same probability of that outcome for the compound lottery and the simple lottery P hat, and this is true for every outcome I equals 1 up to k, then these lotteries, as long as I look at them through the lens of consequentialism, only caring about the outcomes and their probabilities, and I understand probability calculus, you can see that P and P hat are in a sense equivalent, so I should be indifferent between these two lotteries. Let's look at a diagrammatic representation of the reduction axiom, just to further our understanding of this. So here on the diagram, I've represented a compound lottery. In the first stage, we have this yellow chance node, where with some probability PQ1, I receive the lottery Q, in which case there's a chance node where with probability Q of X1, I receive the prize X1, and with probability 1 minus Q of X1, I receive the outcome X2. Similarly, going back to the first chance node, there's a probability P of Q2 that I receive lottery Q2, in which case there is then a probability Q2 of X1 that I receive outcome X1, and a probability 1 minus Q2 of X1 that I receive outcome X2. Okay, so this is a compound lottery. What is the probability that I receive outcome X1 in this case? Well, there are two ways in which I can receive X1. I could receive lottery Q1, so go up the first branch, and then when I arrive at the blue chance node, I could go up again, in which case I receive outcome X1. Or at the first yellow chance node, I could go down and receive lottery Q2, and then go up the orange chance node and receive outcome x1. So there's two ways in which I can receive x1 here. What's the overall probability of receiving outcome x1? It's P of q1 multiplied by q1 of x1. That's the probability of those first two steps, plus P of q2 multiplied by q2 of x1. That's the probability of receiving outcome x1 in the second way, going down the yellow chance node and then up at the orange chance node. Okay, so that's the overall probability of receiving outcome x1 in this compound lottery. Now let's suppose I construct a simple lottery where there is a probability p hat of x1, which is equal to this same probability as the compound lottery offers for receiving outcome x1, and 1 minus this p hat of x2 assigned to outcome x2. Okay, so in terms of the probabilities of receiving each outcome and the possible outcomes offered by these two lotteries, there's a very real sense in which these two lotteries are equivalent. So the reduction axiom says the decision maker should be indifferent between these two lotteries. The next axiom that we will use, axiom 5, is the substitution axiom. Okay, so we're going to phrase this as an axiom for compound lotteries that says the following. Essentially, when I look at a compound lottery, there is some probability of receiving different lotteries. Okay, now let's look at the green lottery here I've labeled with some probability P of QI. I receive a lottery QI. Okay. Now suppose that I'm indifferent between the lottery QI and the simple lottery RI. Well, the substitution axiom says if I create a new compound lottery by taking the compound lottery P and replacing lottery QI by an equivalent lottery in the sense of indifference, replacing QI with RI, then I don't change the decision maker's mind. To see this on a diagram here, let's suppose that our decision maker is indifferent between two simple lotteries, Q2 and R2. Well then, if I look at two compound lotteries, so in the first compound lottery, I have probability P of Q1 of getting lottery Q1. This is the same as the other compound lottery, P of Q1 of getting Q1. And also P of Q3 of getting lottery Q3. That is common to both of these lotteries. So the part that is different between these two compound lotteries, I've coloured in blue here, with some probability P of Q2 on the left-hand side on the left-hand compound lottery, I get lottery Q2, and on the right-hand side, with the same probability P of Q2, I get the lottery R2 instead. While the substitution axiom says, since I like Q2 and R2 exactly the same, I'm indifferent between them, then I will also be indifferent between these two compound lotteries. The final axiom we will use is a technical axiom called the continuity axiom. So this is our axiom 6. What this axiom says is the following. Let's take three lotteries, P, Q, and R, where P is the best, Q is in the middle, and R is the worst. Okay? So it's perhaps easier to understand if you think in terms of strict preferences, although this is also true for the weak preferences that we've written here. So let's imagine that P is strictly better than Q and Q is strictly better than R. Now let's have a look at the compound lottery below. So we've got an alpha probability of receiving the lottery P and a 1 minus alpha probability of receiving the lottery R. Now clearly if alpha was equal to 1, then this compound lottery by the reduction axiom would be exactly the same as lottery P, and so it would be better than Q. if alpha was equal to 0, then this compound lottery would be exactly the same as just receiving the lottery R. What the continuity axiom guarantees is that there is an alpha in between 0 and 1, such that the decision maker is indifferent between the lottery Q and the compound lottery that assigns probability alpha to lottery P and 1 minus alpha to lottery R. Now, continuity axioms like this are very convenient, and they will ensure that the equations that we develop have solutions, and they seem quite natural. However, the downside of continuity axioms is they cannot be falsified by a finite data set. So we couldn't run a laboratory experiment and falsify this condition. Okay, the reason is the condition is saying there exists an alpha in 0, 1 interval. This is a very large interval, 0 to 1. Okay, there are uncountably infinitely many elements in that interval. So while it is possible to find such an alpha to make the experimental subject indifferent between these two lotteries, proving that such an alpha is not there at all would require infinitely many observations, which is more than we can ever take. Okay, so it can't be tested, so we have to assess whether it's a useful assumption. I can guarantee it's useful. It's going to ensure that we're able to construct a utility function, that our equations have solutions, and also whether it's a natural assumption. Okay, now if a preference for risk was not continuous, then there would be some undesirable consequences in terms of behavior. For instance, you would see one lottery being judged infinitely better than another, which leads to the kind of risk preferences where people just refuse to even cross the road or get out of bed in the morning. Okay, so we're going to accept the continuity assumption, knowing that we can't actually test this assumption. So now that we've been through the axioms for choice under risk, the mixture monotonicity axiom, the reduction axiom, the substitution axiom, and the continuity axiom, along with completeness and transitivity, we're ready to state the main result of this lecture, which is the von Neumann-Morgenstern expected utility theorem. This reads as follows. The two following statements are equivalent. So this is an if and only if. Preferences over lotteries satisfy axioms 1 through 6, completeness, transitivity, mixture monotonicity, reduction, substitution, and continuity. If and only if statement 2 is also true, preferences over lotteries can be represented by expected utility. That is, there exists a von Neumann-Morgenstern utility function, little u, defined over the outcomes that turns outcomes into real numbers, such that when we take the mathematical expectation of that those utility values, those von Neumann-Morgenstern utility values, this represents the preferences over lotteries. In the next video, we're going to prove this statement. We're going to prove the more difficult direction, which is that statement 1, assuming the preference axiom holds, implies statement 2. The fact that statement 2 implies statement 1 is much easier. So I would like you to have a go at that as an exercise. Go through each of the axioms that we've developed, substitute the expected utility representation. So assume that preferences are represented by expected utility for simple and compound lotteries, and then show that in each case the axiom must be satisfied simply as an assumption that expected utility represents preferences. In the next video, we will prove the other direction of this famous theorem.